Hi students, in this video we're going to look at how to carry out differentiation using first principles. So at the end of this video you should be able to differentiate simple power functions and polynomial functions from first principles and also interpret the derivative as the instantaneous rate of change. Alright, key things to review. So instantaneous rate of change, that's our rate of change at one particular point on our graph or on our journey or along our function. It is equal to the gradient at that point. So rate of change as a word, it's rate. Mathematically, that's the same thing as gradient or slope of a graph. And then also, as covered recently, the formula for that is our difference quotient, which is given here, where we've got basically up the top here, we've got y2 minus y1. This one here is x2 minus x1, but x2 is x plus h, x1 is just plain x. They cancel to just leave us with h. So this is, in this right-hand side, that's just our gradient formula, right? Rate of change. Then this limit at the start is what makes it instantaneous. We want that h value, that difference between our 2 points, to be as small as possible. That was covered in a previous video. All right, so a new word. So the derivative is a mathematical term for instantaneous rate of change. So from this video onwards, we're going to talk about derivatives, and I want to get us into the habit. Derivatives mean instantaneous rate of change, and that's the word we're going to use almost all the time. In the process of using the difference quotient, to determine the derivative of a function, or instantaneous rate of change, is called differentiation by first principles. Okay, so that's really important. This is called first principles, differentiation by first principles, where we use the difference quotient, okay, to determine our derivative, to determine our instantaneous rate of change. And the derivative, instantaneous rate of change, same thing. We call that f dash x. So if our starting function was fx, then our derivative, well, will be f dash x. All right, so we have to use first principles to differentiate this simple function, our base parabola, x squared. Now we'll start off with our equation. So we have our limit as h approaches 0. That makes our rate of change instantaneous. And we've got our rate gradient formula here on the right. So f of x, well, that's easy. Right, so f of x here, that's just x squared. Now, f of x plus h, we just substitute x plus h into our formula here. So we're squaring x in our first formula. So f of x plus h will be x plus h squared. And then that can be expanded out to this form here. When given a choice, when you're using first principles, always expand if possible. Okay. Possible. It will make collecting like terms a lot easier if you do the expansion. And that's how we can start off. Now, making that substitution, so here, that's f of x plus h, we've substituted in. That one there is f of x, we've substituted in. And now what we notice is that there is some like terms. We've got minus x squared there and positive x squared there. So those terms will be able to cancel out. And so now all we're left with is 2xh plus h squared over h. Now, when you're doing first principles, if you've done this correctly, right, the numerator should only contain terms with a h in it, which these two terms have, 2xh and h squared. That means we're on the right track. We both terms have a h variable in there. Right, now because they both have h terms, and because when we do first principles, the entire numerator should have h terms, we should be able to factorize out h. So if we factorize out h, like we've done in this line here, h out the front leaves 2x plus h in brackets. That's just some simple factorization. Okay, so that's a factorizing step. And then what we can see here is these h's are going to cancel each other out. Okay, h divided by h gives us 1, right? Those terms can cancel each other out, and we're left with the limit as h approaches 0 of 2x plus h. Now, at this point, we're going to apply our limit. So what's going to happen when h approaches 0? Well, this term here will just become 0, and all we'll be left with is 2x. And there's our derivative. This function will give us the gradient, or the instantaneous rate of change of our original function. Now, a couple of notes on this one. Why do we wait till the end to apply the limit? Well, we wait to the end to apply the limit because we've got h in our denominator here. Right? So h in our denominator means it can't equal 0. We can't divide by 0. And so that means we can't apply our limit and say it equals 0 before this last line. What that also means is we have to be able to factorize out h from our numerator too, because we need to be able to cancel out that h in the denominator. So if there's a term in your numerator, after you've done some cancelling, like in this first step, that doesn't involve a h, check your work. You've probably made a mistake. Every term should have a h in it, because you need to be able to factorize in order to cancel out that denominator. Now, what does this result actually mean? So what this means is that for any point on the curve f of x equals x squared, it has a gradient or instantaneous rate of change or derivative, all of those words accurate, of 2x. I'm using that f dash formula there to show we've got the derivative, or that this function is giving the instantaneous rate of change here. Now what we can do then is say, if we want to find the derivative or the instantaneous rate of change of x squared for x equals 4, all we'd have to do is substitute 4 into our derivative function. So substitute 4 in, that's 2 times 4 is 8. So on our parabola here at x equals 2, the gradient of that line, the instantaneous rate of change there, is going to equal 8. And that's how we apply differentiation by first principles to determine an instantaneous gradient. All right, so after this, students, you should be able to differentiate power functions and polynomial functions using first principles, and you should also be able to talk about the derivative as the instantaneous rate of change and use those terms interchangeably.